Hello, and welcome back to the second and main part of our talk. So we will get on with it as soon as I have figured out a way to share my slides with everybody. Perfect. I believe that all of us by now should be able to see the cover slide in front of our screens. Okay, so I have titled today's talk A Very Mild Introduction to Transcendence, and we will get to see what we mean exactly by transcendence in the next couple of slides. Now, our main object of study for today will actually just be the all too familiar real numbers, but with a slight change in perspective regarding the kinds of questions that we are asking about the real numbers. So that being said, a quick disclaimer. I think all of the results, or almost all of the results that we will be encountering today, or the concepts that we will be encountering today, can also, with just minor modifications, be recast in the language of complex analysis. In other words, they can also be extended to talk about complex numbers. They hold for complex numbers as well. But I'm not assuming any background in complex analysis. So we will just be restricting our attention to the set of real numbers. Not much information is lost in any case. All right. So as I mentioned earlier in the introductory part of this series, at the time that Prof. Somani approached me to give this talk, I was still affiliated with the Fields Institute. But at the time of recording the talk, I am only a few weeks away from getting formally affiliated with the University of Pretoria. So it was either I acknowledged neither institution or I acknowledged both institutions. So I chose to go with the safer option. All right, so without wasting any more time, let's just get on with it. All right, so let's just start from the basics and present a setting for what we will be talking about. We'll just start with the natural numbers. So the set of natural or counting numbers, we know them, and then the integers. So these are familiar subsets of the real numbers R. Now, we also have the rational numbers. So the rational numbers are, of course, given as fractions. The numerator is an integer. The denominator is also a non-zero integer. So we give this as quotients of integers. And then from the rational numbers, we have irrational numbers. So the irrational numbers are everything else that is left in the set of real numbers once you take away all the rational numbers. And of course, remember that the rational numbers also include the integers or all the other whole numbers as well. Now, examples of irrational numbers, we've got the square root of 2, the logarithm of 2, pi, e, and the golden ratio, 5, right there in front of us. And typically we identify the irrational numbers as having an infinite non-repeating decimal expansion. And of course, all of these sets combined, or the union of all of these sets, give us back the set of real numbers. So as it is, these are all the numbers that we may have seen one way or another that we are familiar with in our previous studies. And but rather, we also have another classification or another perspective from which we can view the set of real numbers. And this classification is the one that will sort of usher in the subject of today's talk, being transcendental number theory, or an introduction to transcendental number theory. Now, how do we go about this? Well, instead of defining, say, rational, irrational numbers, we have a classification that is typically considered in algebra or number theory in general. We start off by defining the so-called algebraic numbers. Now, algebraic numbers are simply those numbers that we obtain as roots or zeros of polynomials with integer coefficients. So, for instance, the square root of 2 is obtained as a zero of the equation x squared minus 2 equals 0. And of course, the golden ratio, you obtain it by solving the equation x squared minus x minus 1 equals 0. And we also have all manner of algebraic numbers that you can think of. Typically, whenever you obtain a solution of a non-zero polynomial with integer coefficients, then what you obtain is an algebraic number. From there, we move on to transcendental numbers. Now, transcendental numbers are simply all those real numbers that are not algebraic numbers. So these are the numbers that cannot be obtained as zeros or roots or solutions of polynomials with integer coefficients or rational coefficients. It's equivalent. So, for instance, typical transcendental numbers that you may have seen in your studies, of course, one of the most famous transcendental numbers would be pi, as well as e, or Euler's constant. And then pi squared is another example. E to the power 10 is another example. The logarithm of 5 is another example. And e to the pi is another example. As we will see during the talk, it is not easy to actually conclude whether a number is transcendental or not. And we are only able to list these numbers so easily right now because of essentially centuries of progressive work that got us to the stage at which we are at right now in transcendental number theory. So I suppose a bit of a historical explanation. Transcendental numbers were named this way because, in a sense, they actually do transcend algebra. This is in comparison to the algebraic numbers, which we obtain by simple, basic algebraic operations, essentially. That's sort of a little bit of a historical tidbit, I suppose. Now, here's a bit of an exercise for you. We have seen that e to the pi is a transcendental number, or at least if you are to take what I am telling you as a given, then e to the pi is a transcendental number. But what is the nature of pi to the e? Now, what about e plus pi? Is that a transcendental number as well? Well, you'd be surprised to learn that actually we do not as of yet know the answers to these questions, in as much as our intuition tells us that this should actually sort of be evidently or obviously transcendental numbers. We do not as of yet actually have rigorous proofs that these are transcendental numbers. So you can sort of see that even right at the beginning, there are lots of questions that one can ask, which would immediately stump us. Very, very simple sounding questions or problems that one can pose, but then they turn out to be very, very deep or requiring very, very deep techniques to even start working on them. In any case, let us proceed. So we will take a bit of a brief history or timeline of the progress of transcendental number theory. Now, this is not the complete history. I sort of just cherry-picked a couple of monumental results here and there, just so that we can tell the story in a somewhat more concise way that lead us to the main idea behind our talk. So in the 1700s, I would just say it was suspected that some numbers might be transcendental, but none were known as at the time. So around that time, mathematicians suspected that there could be some numbers which you could not express as solutions of polynomials with integer coefficients. but by then there was no specific number that was exhibited to say this is an example of such a number. Now, somewhere in the mid 1700s, Lambert proved that pi is actually an irrational number. And then he conjectured that E and pi might actually be examples of these so-called transcendental numbers that we were looking for. And then I suppose for almost a century, about 90 years or so, there was still many attempts at proving this, but without any success. Around 1844 and 1851, Joseph Liouville proved that transcendental numbers actually do exist. Mind you, he did not work specifically on E and pi, but he sort of answered the first question around here, the one that was suspected in the 1700s. He actually showed that transcendental numbers exist, and he explicitly constructed an example of one such transcendental number, or in fact, a whole family, or he showed a method of constructing a whole family of transcendental numbers, which are, of course, a subset of the real numbers, at least for purposes of our discussion today. Now, we will come back to Liouville and his construction. This is, in fact, one of the main ideas that we will be talking about. But for the sake of progress, around 1873, Charles Hermite actually proved that the number E is, in fact, transcendental, as was suspected about 100 years prior. And then now, in 1874, so just a year later, Georg Cantor proves that the algebraic numbers are actually countable, but the set of real numbers are uncountable. So this is a rather nice and general approach to the topic. So let's just sort of unpack that statement a little bit before moving on. So what does Cantor's result have to do with the existence of transcendental numbers? Well, essentially, what Cantor shows is that you can put on a one-to-one correspondence the set of algebraic numbers with, say, the set of natural numbers. So that's what we mean by countable infinity. And then the set of real numbers cannot actually be put on a one-to-one correspondence with the set of counting or natural numbers. So in a certain sense, there are more real numbers than there are algebraic numbers. So this immediately tells us that, well, after you have counted out all of the algebraic numbers, then what is remaining should be transcendental numbers, since in our classification, we are partitioning the set of real numbers into just two subsets, the algebraic numbers and the transcendental numbers. So this was a very nice monumental result, and this sort of shows a more generalist set theoretic approach to this topic as opposed to the more direct methods that were used earlier. And then in 1882, Lindman proved that a slightly more general result, in fact, a way more general result than Hermite's result here. He proves that for any non-zero algebraic number, alpha, the quantity e to the alpha is transcendental. So this is essentially now giving us a method or machinery or an algorithm, if you will, for constructing transcendental numbers. Take your favorite non-zero algebraic number, plug it into the exponential function, and what you get is guaranteed to be an example of a transcendental number. So, for instance, the square root of 2 is an algebraic number. So Lindman's result tells us that e to the square root of 2 is guaranteed to be transcendental. 3 is an algebraic number, so e to the 3 is an example of a transcendental number. So there are many, many corollaries that we can derive from Lindman's theorem. So you can immediately see that from Lindman's theorem, you can recover Hermite's theorem that E is transcendental. Why? Because E is essentially just e to the power 1, and 1 is an algebraic number. And according to Lindman's theorem, for any non-zero algebraic number, e to the alpha is transcendental. So e to the 1, which is e, is transcendental. But the result is also powerful in the sense that it also now allows us to immediately deduce that pi is a transcendental number by actually taking the contrapositive of Lindman's theorem. So Lindman says that for any non-zero algebraic number, e to the alpha is transcendental, which is equivalent to also saying if e to the alpha is algebraic, then either alpha is transcendental or 0. So given that particular phrasing of the theorem, we know that one of the most famous equations, e to the pi I equals to 1. So 1 is an algebraic number. So what this is telling us immediately is that I times pi is a transcendental number. Now I is an algebraic number, so that tells us that pi is a transcendental number. Multiplying an algebraic number and a transcendental number always produces a transcendental number. So that was sort of a bit of a circle of ideas, but I hope it makes sense. All right, so Lindman's theorem gives us a method of constructing new transcendental numbers, I suppose. And it also allows us to immediately deduce that pi is a transcendental number. So essentially solving two of the classical questions that were at the beginning of transcendental number theory. All right, let us proceed. We will now go back to Liouville's result. Remember, Liouville was the first to actually show that transcendental numbers definitively do exist, or definitely exist. And he actually showed this by giving us an example of one, or a method for constructing a family of such numbers. And these numbers ended up being called Liouville numbers. So in front of us there, we have a definition of what a Liouville number is. So we have that a real number, psi, is called a Liouville number. If for every positive integer n, there is a pair p over q, or a fraction p over q, with q greater than 1, such that the distance from psi, or the distance between psi and p over q, is actually less than 1 over q to the n for every positive integer n. So that's a bit of a mouthful. Let's just spend a bit of time trying to unpack what this definition is actually communicating to us. So what this definition seems to be suggesting is that we are going to define a certain number or a certain subset of the real numbers. And the way we're going to define them, we're going to say, these are numbers that have a very, very good approximation by sequences of rational numbers. But what do we mean by a very, very good approximation by a sequence of rational numbers? Well, we quantify the error that remains in the approximation by the denominator of the approximating irrational number. All right, still that somehow maybe clarifies things a little bit, but it still leaves a whole lot of other questions unanswered. To begin with, why in the world would anyone sort of come up with this definition? Secondly, do such numbers even exist? what if all the real numbers actually do satisfy this? Then this becomes an empty definition. What if none of the real numbers actually satisfies this definition? Then this is also an empty definition. So in summary, what was the motivation for making this definition, for actually isolating the real numbers that have this property? Are there any real numbers that actually do have this property to begin with? So that is the motivation for Liouville numbers. Well, the motivation essentially is Liouville's theorem. And then once we have understood what the theorem is telling us, then it becomes immediately evident or obvious why the definition of Liouville numbers makes sense. And indeed, Liouville numbers do actually exist. We do have answers to all of the questions that we sort of asked ourselves in the past 45 seconds, I suppose. Liouville numbers do exist, and not all real numbers actually do satisfy the definition of Liouville numbers. So this is not an empty definition. It's actually a very concrete, useful definition that led to an amazing result. Okay, so what is Liouville's theorem? Well, Liouville, the result that Liouville started by proving was a result that actually characterized how closely we can approximate algebraic numbers by rational numbers. And then he basically quantifies the quality of that approximation so that any other number that does not satisfy that quality of approximation or that violates that quality of approximation will actually turn out to not be algebraic. So we are also using the type of contrapositive type of reasoning to get what we want. In any case, what is it that Liouville actually proved? Well, we do see the appearance of complex numbers here. Indeed, he proved it at that level of generality, but of course, we can just stick to the real numbers. So let alpha be a real number that is an algebraic number of degree greater than 1. So I think this is the first time in our talk we are encountering the concept of a degree of an algebraic number. But it's not overly too difficult. It's not a difficult concept to understand. Well, the degree of an algebraic number is simply the degree of the polynomial whose root is that algebraic number. It's not quite the formal and exact definition, but for purposes of our talk, to at least communicate the idea behind it, we will take that as our definition for now. Essentially, a number like, say, the square root of 2, we would say it has degree 2 because it is a zero of the equation x squared minus 2 equals 0. Now, that means we have a polynomial of degree 2 whose 0 is our number, which is the square root of 2. And there's no other polynomial with a smaller degree with integer coefficients, which would give us square root of 2 as a solution. That is essentially how we define the degree of an algebraic number. So all rational numbers have degree 1 because they are solutions to essentially linear equations. The number 9/10 is a solution to the equation 10x minus 9 equals 0. So that is a polynomial of degree 1. So all rational numbers can be expressed in that manner, and they are examples of algebraic numbers of degree 1. Any other algebraic number of degree greater than 1 turns out to be an irrational number. So something that I should have mentioned earlier, but which of course appeared to be clear in the first or second slide, is that all transcendental numbers are irrational but not all irrational numbers are transcendental. For example, the golden ratio, the square root of 2, the cubic root of 3, and so on and so on. These are algebraic numbers. So anyway, Liouville tells us that if you have an irrational algebraic number, then you can always approximate it to within a certain distance by rational numbers, but you cannot get any closer than that distance. So basically, he quantifies the degree or the accuracy or the error within which we can approximate an irrational algebraic number by a rational number. And we, of course, once again, quantify that error by the denominator of the approximating rational number. So he essentially gives us a lower bound on how close we can get to approximating an irrational number by a rational number. So once this theorem is established, then we see immediately that if we encounter a number that violates this lower bound, if we encounter a number that essentially violates the inequality in Liouville's theorem, then that number is either a rational number or a transcendental number. Because remember, Liouville's result applies to an irrational algebraic number. So it essentially says if you start off with an irrational algebraic number, then you cannot get within a certain distance of approximating it by a rational number. And of course, with this being said, then the definition of a Liouville number all of a sudden makes sense, because we simply define a Liouville number to be the number that essentially violates the bound that is prescribed in Liouville's theorem. So if we can actually show that such a number exists, then we'll be done, because we'll be knowing that that number is either rational or transcendental. And if we can furthermore show that the number is not rational, then indeed that would be a genuine example of a transcendental number. So that was sort of the circle of ideas that led to the definition or construction of Liouville numbers, and therefore the first exhibition of a transcendental number way back then. So here's an example of a Liouville number. So the so-called Liouville's constant, and I believe we are all familiar with infinite sums. So essentially, if you just sum 1/10 to the n factorial, the number that you get is an example of a Liouville number. And in fact, this is the so-called Liouville constant. And beneath that, I have given a slightly more general method of constructing similar numbers, which of course are Liouville numbers and therefore transcendental numbers. So you could basically say that you can play around with the numerators and denominators in your summons here to still produce more Liouville numbers. So essentially, you could replace the 1 with some number an or some sequence an, and you could replace the 10 in the denominator with some fixed number or constant b, as long as b is greater than, at any given point in time, your denominator is greater than any of the numerators above here, then you will get a Liouville number. That's sort of the more general construction of a Liouville number as well. Now that we have seen Liouville numbers and an example of, a transcendental number, we will go back to Lindman's theorem. Remember that Lindman proved that e to the alpha will always be transcendental for any non-zero algebraic number alpha. But another corollary of Liouville's theorem is that if alpha is an algebraic number, then the logarithm of alpha, the sine of alpha, arcsine of alpha, the hyperbolic sine of alpha, essentially all the trigonometric functions as well as their hyperbolic counterparts, when evaluated at an algebraic number, they are all transcendental. So this is not too difficult to deduce. Once you encounter complex analysis, you will see that all of these functions can actually be expressed in terms of the exponential function e to the z. They can all be expressed either in terms of the exponential function or the inverse of the exponential function being the logarithm function. So, and in fact, the way they are expressed is in terms of rational functions or polynomials in e to the z and e to the minus z combinations of that. So once you are aware of that, it's not a very huge leap to go from the original Lindman's theorem that e to the alpha is algebraic to then concluding that the logarithm of alpha will also be algebraic. The other trigonometric functions evaluated at alpha will also be transcendental rather. So yes. So that's a corollary of Lindman's theorem that is actually now leading us to the main idea or the main concept that I wanted to share with you for this talk. And this concept essentially brings together sort of the two worlds that we have considered here within transcendental numbers. On the one hand, we have what I would say, or what I would call the Lindman's world, whereby we are generating transcendental numbers through the exponential function. On the other hand, we have a Liouville's world, where we have this other method of generating other genuinely different transcendental numbers. And we bring these two worlds together in the form of a question. Well, once again, to reiterate, Lindman tells us that e to the alpha is transcendental when you plug in an algebraic alpha, non-zero, of course. But what if instead of taking your alpha as an algebraic number, you take your alpha as a Liouville number? Now that we are familiar and we are experts on Liouville numbers, of course. So here's the question. Suppose now that alpha is a Liouville number. Is e raised to the alpha a transcendental number? How about the logarithm of alpha, the sine of alpha, the arcsine of alpha, sinh of alpha, where once again alpha is a Liouville number? So that is a sort of a natural question to sort of ask, especially given the preamble or preparation that we have sort of put in place here. It's sort of natural from the perspective of we basically created a setup to ask this question, essentially. So what would be the answer to this question? Well, in order to answer this, we sort of have to take a quick detour, and the answer is almost an immediate corollary of this detour that we are going to take. And without wasting any more time, let's take a very, very quick discussion of Moller's classification. Well, what is Moller's classification? So around 1932, Kurt Moller found another partitioning of transcendental numbers into three classes. I suppose this is also maybe the first time that we are probably encountering the word partition. So a partition of a set is essentially just a separation of the set into disjoint subsets. So you start off with a set, and then you essentially separate it into disjoint subsets or a collection of subsets such that the intersection of each of those subsets is empty. So this is indeed intuitively what you'd consider an actual separation of a set. That's sort of an informal definition of what we mean by a partitioning. So essentially now what we mean here is that, well, we know when we have the real numbers, they fall into two classes, the algebraic numbers and the transcendental numbers. We can put aside the algebraic numbers and now just focus on the transcendental numbers. Moller tells us that, well, we can take the set of transcendental numbers and further separate it into three disjoint classes. There is a way in which we can define some concept such that when we apply this concept to transcendental numbers, they sort of fall into three, they sort of naturally fall into three separate classes that are disjoint. But it was a very deep theorem, a very, very technical theorem. So, of course, for purposes of our talk here, I will not put the theorem or exhibit the actual result on our slides, but we should at least understand the moral behind it, or the corollary, at least, or some facts that we can derive from this rather powerful method and classification scheme that was constructed by Moller. But if you are curious anyway, the way we go about partitioning the set of transcendental numbers into these classes is still related to the quality of their approximation by algebraic or even rational numbers. So this was sort of a vast generalization or a vast improvement on Liouville's theorem or Liouville's definition. So that's pretty much all it is, right at the heart of it. The rest are sort of just actual technicalities in how to properly do that in a consistent manner. All right, but there are a few aspects about Moller's classification that we need in order to address our question here about exponentials of Liouville numbers. So one, or the first fact that we should keep in mind is that if you have two numbers that are algebraically dependent, then they belong to the same Moller class. I'm not sure if we are familiar with the concept of algebraic dependence, but of course, through our encounter with linear algebra, we know what linear dependence or linear independence means, at least in terms of vectors in a vector space. But we say two numbers are algebraically dependent, or we say two numbers are algebraically independent if you cannot find a polynomial with two variables, p of xy, and integer coefficients, such that when you plug in those two numbers, you get a 0. So this is sort of a generalization of from some perspective, it is a generalization of linear dependence or independence, at least in the case of numbers, real or complex numbers. And it is also actually a generalization of what we mean for a number to either be algebraic or transcendental, except that in this case, we are now looking at a set of numbers more than just one number. And instead of saying, is this number algebraic or transcendental, we are saying, are these two numbers algebraically dependent or algebraically independent? So in any case, if we have two numbers that are algebraically dependent, then the main power of Mollar's classification is that these two numbers will belong to the same class. So even if you do not know what class they belong to begin with, you know that they'll be together in that class anyway. So for instance, pi and pi squared, they are algebraically dependent, so they'll belong to the same class, even if we do not know which class within the Molar classification does pi belong to. All right. Now, here's another corollary or that sort of falls off from Mollar's classification. It says that if you have a non-zero algebraic number, then e to the alpha actually belongs to the class S. So Molar named his classes S, T, and U. And a piece of history there says that, well, he chose the letter S because this was the first letter of his advisor's last name. I think he was advised by Ziegel. So, and then of course, T and U are just the next two letters in the alphabet. But so it turns out that according to the definition that Molar made, or according to his classification scheme, the exponential function sends all the algebraic numbers to the class S. Now, according to that definition, our set of Liouville numbers, actually the set of Liouville numbers, is a proper subset of the class U. So remember, that also means that Liouville numbers are, you cannot find any Liouville numbers in the class S or the class T. So we just have to bear all these facts in mind. Liouville numbers belong to the class U. The exponential function sends algebraic non-zero numbers to the class S. And if two numbers are algebraically dependent, they should fall into the same class. All right, that being said, now we can proceed to what's attempting to answer our question. So indeed, I have actually, in the lower part of the slide, included a few notes about the definition of our algebraic dependence or independence, just in case it was the first time we encountered it. And indeed, we said two numbers A and B would be algebraically dependent if and only if we can find a non-zero polynomial with two variables or in two variables, such that P of AB is 0. And this polynomial should be having integer coefficients. And I said, indeed, note that the numbers do not necessarily have to be algebraic in order to be algebraically dependent. And we give an example there. For instance, if you take x as the square root of 2 times pi and y as pi squared, these two numbers are transcendental to begin with, but they are algebraically dependent. Why do we say that? Well, we can actually find a non-zero polynomial such that when we plug in x and y, we actually get the final answer being 0. And we have that polynomial right there in front of us. It's the polynomial p of xy equals x squared minus 2y. So indeed, if you are to plug in x into this polynomial and you plug in y into the polynomial, you should get 0 as your solution. All right. Perfect. So indeed, we can now finally consider the answer to our question about the one that brought together the world of Liouville numbers and the world of exponential functions, so to speak. Now, here's a theorem. And the theorem, essentially, it's sort of part of joint work with Sidney Morris that sort of came out last year in 2022. But indeed, we sort of mentioned this in passing or obtained this as a corollary of some other concept that we were looking at. But essentially, here's a result. Let alpha be a Liouville number, or in fact, since we are now familiar with Moller's classification, you can say, suppose alpha is a number that belongs to Moller's class U, but let's just say a Liouville number. Then the following numbers defined in terms of alpha are transcendental. E to the alpha will be transcendental, and then I said trig of alpha and the hyperbolic trig of alpha. Well, I used the word trig here, or the acronym TRG here, just to represent a generic trigonometric function. So trig would mean either sine, cos, or tan of alpha, and trig H, of course, would be, it represents sine, cos, or tan hyperbolic of alpha. The logarithm of alpha would also be transcendental, and the arc functions of our trigonometric functions, arc sine, arc cos, arc tan, together with their hyperbolic counterparts, will also be transcendental when these functions are evaluated at a Liouville number argument, essentially. So, and the proof is actually not that it's straightforward, but indeed, as you will see, all of the heavy lifting in this result is done by Moller's classification. So indeed, this was essentially just really sort of just a slight little trick to sort of answer this question. Basically, Moller's classification does all the heavy lifting, and it pretty much answers the question for us. One just needed to sort of just flesh it out a bit. But in any case, we can pick one of these functions here and show how to derive such a result. And I suppose from your linear algebra, you have encountered the proof by contradiction technique. So this is what we're going to use here. We'll start off by assuming the opposite of what we would like to prove, and then show that we end up getting a contradiction with something that we know already. All right, so we can do this for the arc sinh alpha, so the arc of the hyperbolic sine of alpha. So our claim is that if alpha is a Liouville number, then arc sine hyperbolic of alpha should be transcendental. So suppose not. So we can just call it mu. We can say, yeah, let alpha be a Liouville number, but suppose mu, which is arc sinh alpha, is algebraic. It's an algebraic number and not a transcendental number. Then, and this is at least, I suppose, the part where we used the thing or the concept that we're going to encounter in complex analysis, that these trigonometric functions and their hyperbolic counterparts can all be expressed either in terms of the exponential function or the logarithmic function. So as it turns out, arc sinh of alpha is actually equal to the logarithm of alpha plus, well, square root of alpha squared plus 1. So these two are actually equal. So arc sinh of alpha can be expressed in terms of this logarithm. So that means mu, which is equal to this logarithm, would be algebraic. So we are saying mu is algebraic, and what do we know? We know that according to Moller's classification, e to the mu should be an S number, and we have it right here in terms of Moller's classification. If alpha is algebraic, then e to the alpha belongs to S. So we've assumed mu is algebraic, so e to the mu should belong to S. But e to the mu, once we raise mu to e, the logarithm disappears. So it is telling us that this number here, alpha plus square root of alpha squared plus 1, is an S number. And of course, bear in mind or remember that alpha is assumed to be a Liouville number. Now, we are saying this number that is defined in terms of the Liouville numbers belongs to S. So proceeding, on the other hand, if I let x be alpha and I let y be alpha plus square root of alpha squared plus 1, then turns out that x and y are actually algebraically dependent. So in fact, x and y satisfy this polynomial here, y squared minus 2xy minus 1 equals to 0. This is a polynomial in two variables with integer coefficients. And you can try it out for yourself by plugging in x and y, as they're defined here, into this polynomial, and you'll see that they evaluate to 0. But the main idea, or the main point being that alpha and this number are algebraically dependent. And what is it that we know about Moller's classification? If two numbers are algebraically dependent, then they belong to the same class. So this is telling us that alpha, remember, which is our Liouville number, together with y, which is e to the mu, are algebraically dependent. So in other words, this is telling us that e to the mu, which is the number y here, belongs to u. Why? Because our alpha is a Liouville number, and we know that Liouville numbers belong to the set u. So we actually now have a contradiction here, because on the one hand, we somewhere through our argument derived that e to the mu belongs to s. But finally, we also concluded that e to the mu belongs to u. But we know that u and s are disjoint classes, and we have a contradiction. So that means that our first supposition here was indeed wrong, and therefore we conclude that mu should be transcendental when mu is arcsync of alpha, and alpha being a Liouville number, or in general a u number. So there was a lot to say, but essentially it basically addresses this question that we asked here. If you take the exponential function and you evaluate it at the Liouville number argument, is what you get in algebraic or transcendental number. So what we have shown is that what you get is always a transcendental number. But this is essentially only the beginning of the story if one is maybe interested in this particular direction, because one can start asking even more follow-up questions that are actually way more deeper. For instance, well, we know that e to the alpha indeed will be a transcendental number, where alpha is a Liouville number. But can e to the alpha be a Liouville number to begin with? In other words, could you take e, raise it to a Liouville number, and the resulting transcendental number is also some other Liouville number? So that is an interesting question, fascinating question. And I believe that, yes, in some, actually the result is known. I think this was a result by K. Santel Kumar together with Michelle Waldschmidt. It is known that in some instances, yes, for some Liouville numbers, actually the answer is yes. We do not know, yeah, of course it's not for all Liouville numbers, but for some Liouville numbers you could get that. But you could also just sort of ask, starting with a Liouville number, if you plug it into the exponential function, where is the result going to fall in the Molars classification? Will it be a U number? Will it be an S number or a T number? And other questions related to that can also be asked. So indeed, this is just the beginning of, I suppose, another possible direction of study. But for now, I will stop here. This is all that I wanted to share with you today. And I will see you guys again shortly in the Q&A section of our talk. All right. So thank you, and I will see you guys soon.